Deep Space Exoplanet Exploration. Quiet Worlds of Water and Ice, a sleep video script for relaxation and wonder. Welcome, dear traveler, to a journey beyond the familiar shores of our own world. Tonight, as you settle into stillness and allow your breathing to slow, we will drift together through the cosmos, exploring distant planets where water flows in forms both familiar and strange. This is a place of quiet contemplation, where the vastness of space becomes a gentle companion to your rest. Close your eyes if you wish. Let the weight of the day fall away from your shoulders. There is nothing you need to do now but listen and breathe. The universe is patient, and so are we. In the hours ahead, we will visit worlds wrapped in ice, planets where ancient oceans may hide beneath frozen shells, and distant spheres where water vapor rises like mist into alien skies. These are the quiet worlds of water and ice, and their stories are written in starlight. Let us begin. Take a deep breath in now. Feel the air fill your lungs, carrying oxygen that was made by ancient stars. Hold it for a moment, then release it slowly, letting tension flow out with it. The water in your body, the very substance that makes life possible, was forged in the hearts of dying stars and delivered to Earth billions of years ago. You are quite literally made of star stuff, and the water that flows through your veins connects you to every water world in the cosmos. Another breath, slower this time. Feel the weight of your body settling into wherever you rest. There is nothing to do, nowhere to go, nothing to worry about. Just breathe and listen, and let the wonders of the universe wash over you like gentle waves on a distant shore. The journey we are about to take will last for several hours. You may fall asleep at any point, and that is perfectly fine. The story will continue, a gentle river of words flowing through your dreams. When you wake, whether in minutes or hours, the cosmos will still be there, patient and eternal, waiting to share more of its secrets. Segment 1. The search begins. In the grand tapestry of the cosmos, we find ourselves drawn to a profound question that has echoed through human consciousness for millennia. Are we alone? And if life exists elsewhere, where might it flourish? The search for answers has led scientists to look beyond our own solar system, to planets circling distant stars in the endless night. This is the essence of exoplanet exploration, a quest to understand worlds that orbit suns other than our own. Exoplanet exploration seeks to understand planets orbiting stars outside our solar system. Think of it for a moment. Every point of light you see in the night sky is a star, and around many of those stars, planets are turning in their own patient orbits. Some of these worlds are giants of gas, swirling with storms that could swallow Earth many times over. Others are small and rocky, perhaps not so different from the ground beneath your feet on a summer evening. And among all the qualities we might search for on these distant worlds, one substance captures our attention above all others: water. The molecule that fills our oceans, falls as rain upon our forests, and courses through our own bodies. Water, in its endless dance between liquid, solid, and gas, is the foundation of life as we understand it. These worlds can carry water in various forms, including ice and vapor. Imagine a planet where frozen plains stretch to every horizon, where ice mountains rise in silence beneath unfamiliar constellations. Or picture a world shrouded in steam, where water vapor drifts through an atmosphere thick with possibility. These are not merely fantasies. These are the kinds of worlds we are beginning to find scattered throughout our galaxy like hidden treasures waiting to be discovered. The methods we use to find this water are as elegant as they are ingenious. Detecting water ice around white dwarfs involves observing at specific infrared wavelengths. White dwarfs are the remnants of stars like our Sun, ancient embers that still glow with enough heat to reveal their secrets. When we point our instruments toward these stellar remnants, we can sometimes detect the telltale signatures of ice in the debris that surrounds them. One particular feature holds special promise in this search. The 44-micron water ice feature is promising for the observation of icy disks. This refers to a specific wavelength of infrared light that water ice absorbs in a distinctive way. When astronomers observe this wavelength, they can identify ice even across the vast distances between stars. It is like having a cosmic fingerprint, a unique signature that says, yes, water is here. Of course, our current instruments can only see so much. The universe is vast, and our eyes, even when extended by the most powerful telescopes, have limitations. But the future holds tremendous promise. Future missions like Prima will improve our ability to detect water vapor and ice in distant disks. Prima, which stands for Probe Far Infrared Mission for Astrophysics, represents the next generation of space-based observatories. With its enhanced capabilities, we will peer deeper into the cosmos and find water in places we cannot yet imagine. Already we have identified promising places to look. Many white dwarfs within 60 parsecs could host detectable icy disks. A parsec is a measure of cosmic distance, roughly 3.26 light-years. 60 parsecs, then, represents a sphere of space encompassing our cosmic neighborhood, a region where thousands of white dwarfs drift through the darkness. Among these ancient stars, some may be surrounded by the frozen remnants of planetary systems, icy graveyards that whisper of water worlds that once existed. The detection of water is not limited to finding ice. Water ice vapor can also be detected through rotational lines in the infrared spectrum. When water molecules spin and tumble in space, they emit and absorb light at very specific frequencies. By analyzing these spectral lines, astronomers can identify water vapor, even when it exists as a thin, ethereal presence in the cold reaches of space. To accomplish these observations, we need the most sensitive instruments humanity has ever created. Observations can be made with enhanced far-infrared spectrometers like Prima. A spectrometer is essentially a device that separates light into its component wavelengths, like a prism creating a rainbow from sunlight. But far-infrared spectrometers work with light that human eyes cannot see, light that carries information about the coldest and most distant objects in the universe. As you rest here, breathing slowly, consider how remarkable it is that we can detect water across such unimaginable distances. The light that carries this information has traveled for years, decades, even centuries before reaching our instruments. And in that light, written in wavelengths our eyes will never perceive, is the story of water in the cosmos. But our search for water is not limited to distant stars. Much closer to home, on our own moon, researchers are developing radar instruments to find buried water ice. The moon, that familiar companion that has watched over human dreams since the dawn of our species, may harbor secrets beneath its dusty surface. Hidden in permanently shadowed craters near the lunar poles, water ice may have accumulated over billions of years, preserved by the eternal cold. The method being developed to find this buried treasure is surprisingly elegant. Cosmic rays can generate radar waves that bounce off subsurface ice, revealing hidden water deposits. Cosmic rays are high-energy particles that stream through space from distant explosions and violent events. When these particles strike the lunar surface, they can create brief pulses of radio waves. These waves penetrate the soil and reflect off buried ice, creating echoes that sensitive instruments can detect. Why does this matter? Why should we care about ice hidden beneath the moon's surface? The answer lies in the future of space exploration itself. Detection of lunar water ice can help sustain future lunar missions. Water is heavy, and launching it from Earth is enormously expensive. But if we can find water on the moon, we can use it to support astronauts, to grow food, and even to create rocket fuel. The moon's ice could become a stepping stone to the stars. And so, as you drift here in this peaceful moment, know that the search for water unites our nearest celestial neighbor with the most distant reaches of the observable universe. From the craters of the moon to the dying glow of ancient white dwarfs, water is there, waiting to be found. And in finding it, we take our first steps toward understanding whether life, in some form, might flourish beyond the gentle blue sphere we call home. Let your thoughts drift now, like water vapor rising into an alien sky. There is no hurry. The cosmos has been waiting billions of years for us to begin this search. A few more moments of rest will change nothing and give you everything you need. The stars that shine above you tonight have been shining for millions, even billions of years. They have watched over the formation of planets, the condensation of water, the first stirrings of life on countless worlds. What stories might they tell if they could speak? What wonders have they witnessed in their long, patient vigil? Perhaps one of those stars is home to a water world where life has found a way to flourish. Perhaps right now, as you rest here, beings on that distant world are looking up at their own night sky, wondering the same things you wonder. The search for water is, in some ways, a search for connection. Water is the great universal solvent, the medium in which life on Earth arose and evolved. When we find water elsewhere, we find the possibility that we are not alone, that life may be a cosmic phenomenon rather than a terrestrial accident. This possibility fills us with wonder and humility in equal measure. Breathe in again now. Feel the rhythm of your breath, the ancient pattern that connects you to all living things. Exhale and let go of any remaining tension. You are safe here. You are held by gravity, by atmosphere, by the gentle embrace of a planet that has nurtured life for 4 billion years. And somewhere out there, other planets may be doing the same, cradling their own forms of life in oceans we are only beginning to imagine. Segment 2. signs of distant oceans. As we continue our journey through the cosmos, we turn our attention to one of the most tantalizing possibilities in the search for life beyond Earth: the existence of liquid water on exoplanets. Not ice, not vapor, but water in its most life-sustaining form, flowing and pooling on alien shores beneath alien suns. This is the dream that drives countless astronomers to spend their nights gazing at distant stars, hoping to catch a glimpse of something extraordinary. On exoplanets, scientists seek techniques to identify liquid water, a key ingredient for life. This search is not straightforward. We cannot simply point a telescope at a distant world and see its oceans glittering in starlight. The planets we study are so far away that they appear at best as tiny fluctuations in the light of their parent stars. And yet, from these subtle variations, we can learn remarkable things. One of the most promising approaches involves looking not directly at water, but at its effects on a planet's atmosphere. A decrease in atmospheric carbon dioxide may indicate the presence of surface oceans. This may seem counterintuitive at first. How can the absence of one gas tell us about the presence of water? The answer lies in the chemistry that occurs when water and carbon dioxide meet. Water dissolved in oceans could sequester atmospheric carbon dioxide, providing clues to liquid water on exoplanets. On Earth, our oceans absorb enormous quantities of carbon dioxide from the atmosphere. The gas dissolves into the water and eventually becomes locked away in carbonate minerals on the ocean floor. This process has regulated our planet's climate for billions of years. If we observe a rocky planet with unexpectedly low levels of atmospheric carbon dioxide, it might suggest that oceans are present, quietly absorbing the gas just as Earth's oceans do. We are fortunate to live in an era when such observations are possible. Current telescopes like JWST can measure atmospheric carbon dioxide levels to infer surface water. The James Webb Space Telescope, humanity's most advanced eye on the universe, has the sensitivity to analyze the atmospheres of planets orbiting distant stars. By measuring the amounts of various gases, including carbon dioxide, scientists can begin to piece together the conditions on these far-off worlds. But carbon dioxide is just one piece of the puzzle. Detecting water vapor, ice, and clouds on exoplanets helps assess their habitability. Each form of water leaves its own signature in the light that reaches our instruments. Water vapor produces certain absorption patterns. Ice creates others, and clouds of water droplets scatter and reflect light in distinctive ways. By carefully analyzing all these signatures, we can build a picture of what a planet's surface and atmosphere might be like. The amount of data involved in this analysis is staggering. Every observation produces vast quantities of information that must be carefully processed and interpreted. This is where new technologies come to our aid. Machine learning algorithms can aid in identifying water signatures in exoplanet data. These sophisticated computer programs can sift through enormous datasets, finding patterns that human researchers might miss. They learn from examples, becoming better and better at recognizing the subtle signs of water in alien atmospheres. By analyzing spectral data, scientists can distinguish ice, water vapor, and clouds on distant worlds. Spectral data is essentially the fingerprint of light. when starlight passes through or reflects off a planet's atmosphere, certain wavelengths are absorbed while others pass through. By studying which wavelengths are missing or diminished, we can determine what substances are present. It is like identifying a song by the notes that are played and the silences between them. The appearance of a planet can also tell us about its water. The reflectance and color of exoplanets can reveal surface features like oceans and ice caps. A world with vast oceans would appear different from one covered in desert or forest. Ice caps would be highly reflective, while liquid water would absorb certain wavelengths and reflect others. Even from light years away, these differences can potentially be detected. To make sense of these observations, scientists create detailed computer simulations. Advanced algorithms can simulate different surface and atmospheric compositions to interpret observations. These simulations model how light would interact with various combinations of water, ice, rock, and gas. By comparing real observations to simulated ones, researchers can narrow down what conditions might exist on a distant planet. Not all detection methods involve direct observation of water itself. Indirect methods, such as high albedo reflections, help identify planets with resurfaced ice or water. Albedo is a measure of how much light a surface reflects. Ice has a very high albedo, meaning it reflects most of the light that strikes it. If we observe a planet that is unexpectedly bright, it might indicate that the surface is covered in fresh ice, perhaps recently deposited by some geological process. Changes in a planet's brightness over time can be especially revealing. Variations in reflectance spectra may suggest cryovolcanism or resurfaced icy worlds. Cryovolcanism, which we will explore more deeply later in our journey, is the eruption of water and ice from a planet's interior. If we observe a world becoming brighter over time, it might indicate that fresh ice is being deposited on the surface through volcanic-like activity. Rest now, and let these ideas settle like snowflakes drifting down through an alien atmosphere. The search for water on distant worlds is patient work, conducted across years and decades. The planets we study have existed for billions of years, and they will continue their silent orbits long after we have turned our attention elsewhere. There is a certain peace in this knowledge. The universe proceeds at its own pace, indifferent to our hurry, generous in its mysteries. Picture yourself now on the surface of an exoplanet, if such a thing were possible. Perhaps you stand on an ice shelf, looking out across a frozen sea. The sky above is tinged with unfamiliar colors, lit by a star that is not our sun. In the distance, mountains of ice rise against the horizon, their peaks catching light in ways that seem almost magical. This world has been here for billions of years, and it will be here for billions more. Its patience is absolute, its silence profound. Or perhaps you float in the atmosphere of a different world, a warm water planet where clouds of vapor drift past. Below, glimpsed through breaks in the clouds, an ocean stretches endlessly in all directions. No land interrupts its expanse. Waves roll beneath you, driven by winds you cannot feel, shaped by forces you cannot see. This ocean may be deeper than any on Earth, and it may have existed since this planet first formed. What secrets does it hold in its depths? What forms of life might swim through its waters? These imaginings are not idle fantasy. They are informed speculation, based on the data we gather from telescopes pointed toward distant stars. The exoplanets we study are real. Their oceans, if they exist, are real. Somewhere in our galaxy, perhaps not so far away in cosmic terms, worlds like these may be waiting to be discovered. Segment 3. Transits and atmospheres. When a planet passes in front of its star, it creates a moment of extraordinary opportunity. For a brief time, starlight filters through the planet's atmosphere before reaching our telescopes. In that filtered light, we can read the secrets of worlds we will never visit. This is the magic of transit observations, and it has revolutionized our understanding of exoplanet atmospheres. The detection of gas absorption features during transits can indicate the presence of water vapor. As starlight passes through a planet's atmosphere, gases absorb specific wavelengths. Water vapor, with its distinctive molecular structure, leaves a clear signature in this absorbed light. By carefully measuring what wavelengths are diminished during a transit, we can determine whether water vapor is present in the atmosphere above. Exoplanet atmospheres can be analyzed through transmission spectroscopy during transits. Transmission spectroscopy is the technique of studying light that has been transmitted through an atmosphere. Think of it like holding a colored glass up to the sun. The color of the glass changes the light that reaches your eyes. In the same way, a planet's atmosphere changes the starlight that passes through it, and from these changes, we can learn what the atmosphere contains. Some planets reveal themselves to be remarkably active. Some exoplanets show signs of high water vapor output, hinting at active cryovolcanic processes. These are not static, frozen worlds, but dynamic places where internal heat drives the eruption of water and ice. The water vapor we detect may be freshly ejected from the interior, evidence of geological processes that continue even now as we observe from our distant vantage point. The Hubble Space Telescope has observed water signatures on distant rocky planets. Hubble, which has served humanity faithfully for over 3 decades, continues to make groundbreaking discoveries. Its observations have confirmed that water exists on planets beyond our solar system, turning speculation into scientific fact. Each detection adds to our understanding of how common water might be among the countless worlds in our galaxy. One particularly exciting discovery involves a planet known by its catalog designation. GJ9827d is one such planet where water molecules were detected during multiple transits. This world orbits a cool red dwarf star roughly 97 light-years from Earth. Over multiple observations, astronomers detected the unmistakable signature of water vapor in its atmosphere. It was a moment of quiet triumph, another confirmation that water is present beyond our solar system. The presence of water also tells us something about how these planets formed. Water-rich atmospheres suggest formation far from their host stars where ice can condense. In the cold outer reaches of planetary systems, beyond what astronomers call the snowline, temperatures are low enough for water to exist as solid ice. Planets that form in these regions can accumulate vast amounts of water ice during their formation. Later, they may migrate inward toward their stars, carrying their water with them. This has profound implications for the search for habitable worlds. Exoplanets with water signatures are prime targets in the search for habitable worlds. When we find a planet with water in its atmosphere, we know that this essential ingredient for life is present. It does not guarantee that life exists, but it tells us that at least one necessary condition has been met. These worlds become priorities for future study, candidates for the intense scrutiny that might one day reveal signs of biology. The forms water takes on these planets are diverse and fascinating. Water on exoplanets can exist in vapor, liquid, or ice phases, each detectable through different methods. Vapor leaves absorption signatures in transit observations. Liquid water might be inferred from climate models or from the detection of dissolved gases like carbon dioxide. Ice creates distinctive reflectance patterns and infrared signatures. Each phase tells a different part of the story of water on a distant world. Techniques for water detection include transmission spectroscopy and direct imaging. Transmission spectroscopy, as we have discussed, examines light passing through an atmosphere during a transit. Direct imaging, by contrast, attempts to capture actual images of planets separate from their stars. This is extraordinarily challenging because planets are so much dimmer than the stars they orbit. But advances in technology are making it increasingly possible. Direct imaging can reveal reflectance spectra indicative of surface oceans. When we manage to capture light reflected from a planet's surface, we can analyze that light to learn about the surface itself. Oceans of liquid water would have distinctive reflective properties, different from rock or ice or vegetation. If we can isolate enough light from a planet's surface, we might one day see the spectral signature of an alien ocean. As you rest here, breathing slowly and steadily, consider how much we have learned in just a few decades. When the first exoplanet orbiting a sun-like star was discovered in 1995, we knew of no worlds beyond our solar system. Now we have confirmed thousands, and we have analyzed the atmospheres of dozens. The pace of discovery continues to accelerate, and with each passing year, we learn more about water in the cosmos. The presence of ice and vapor influences the planet's albedo and climate. Albedo, as we discussed earlier, describes how much light a surface reflects. A planet covered in ice would be very reflective, while one covered in dark ocean water would absorb more heat. Water vapor in the atmosphere acts as a greenhouse gas, trapping heat and warming the surface. The interplay between these factors determines what conditions might exist on the surface below. Close your eyes now, if they are not closed already, and imagine yourself drifting among these distant worlds. Each one is unique, with its own story of water and ice, its own history stretching back billions of years. Some may be harsh and hostile, their water locked in forms that cannot support life. Others may be gentle, with conditions remarkably similar to Earth's. We are only beginning to read these stories, and the chapters ahead promise wonders we cannot yet imagine. The act of transit observation is itself a kind of meditation. Astronomers wait patiently for a planet to cross the face of its star, an event that may last only hours out of an orbital period of days or weeks or months. During this brief window, they gather data, measuring the subtle dimming of starlight as the planet passes. It requires patience, precision, and a willingness to work with incomplete information. In many ways, it mirrors the kind of contemplative awareness we practice when we meditate or prepare for sleep. We observe, we note, we let the information come to us in its own time. The data gathered during a single transit may be inconclusive. It is only through repeated observations across many transits that patterns emerge and certainties form. This is the nature of scientific inquiry: slow, methodical, humble in the face of uncertainty. And yet, through this patient work, we have confirmed the presence of water vapor on worlds light years away. We have identified planets that may harbor oceans, moons that may hide liquid water beneath their ice. Each discovery is a triumph of human curiosity and perseverance. Segment 4: Icy Moons and Cryovolcanism. In our own solar system, some of the most intriguing places in the search for life are not planets at all, but moons. These icy satellites orbit the giant planets Jupiter and Saturn, and beneath their frozen surfaces, they may harbor oceans of liquid water. Understanding these nearby worlds helps us recognize similar environments among the distant exoplanets we study. Cratered, icy worlds are similar to some moons in our solar system, such as Europa and Enceladus. Europa, a moon of Jupiter, presents a surface of cracked and ridged ice, like a frozen sea that has been disturbed by unseen forces below. Enceladus, orbiting Saturn, is even more dramatic, with geysers of water ice erupting from its south pole into space. These moons remind us that water can exist in surprising places, hidden beneath shells of ice, far from the warmth of the sun. These worlds are likely to have high water vapor outputs through cryovolcanic eruptions. Cryovolcanism is a process where icy planets or moons erupt water and other volatiles. Unlike volcanoes on Earth, which spew molten rock, cryovolcanoes erupt mixtures of water, ammonia, and other substances that are solid at normal temperatures but can become liquid under the right conditions. When these materials reach the surface, they freeze almost instantly in the cold of space, creating plumes of ice crystals. The scale of these eruptions can be measured. High H2O column densities during eruptions can be detected via spectral signatures. Column density refers to the amount of a substance in a column of space extending upward from the surface. During an eruption, the column density of water vapor spikes dramatically, and this spike can be detected through careful spectroscopic observation. It is like watching a geyser erupt, but from millions of miles away, seeing only the subtle changes in light that the eruption produces. These eruptions are not steady. They vary over time, and these variations tell us about the internal workings of these worlds. Variability in water vapor output can inform us about geological activity on icy worlds. If we observe a moon or planet and see its water vapor output changing, we know that something is happening beneath the surface. The internal heat that drives these eruptions may wax and wane, perhaps influenced by tidal forces from nearby planets. To study these variations, astronomers employ multiple approaches. Direct detection efforts focus on high-contrast spectra captured by telescopes. High-contrast spectroscopy attempts to separate the faint light from a moon or planet from the overwhelming glare of its nearby star or parent planet. This requires incredibly precise instruments and careful data processing, but the rewards are substantial. When successful, These observations can reveal the composition and behavior of cryovolcanic plumes. Not all evidence of water activity is detected directly. Indirect detection methods include observing anomalously high reflectivity, hinting at resurfacing. When a world's surface is being continually refreshed by cryovolcanic deposits, it tends to be brighter than older weathered surfaces. This brightness can be detected from afar, suggesting that something is actively renewing the surface. The atmospheres of water-rich worlds have distinctive characteristics. Cloudy, water-rich atmospheres produce specific spectral features. Clouds of water ice or liquid droplets scatter light in particular ways, and they absorb and emit radiation at specific wavelengths. By analyzing these features, scientists can determine not just whether water is present, but in what form and in what quantities. The detection of water on exoplanets extends to planets orbiting stars other than the Sun. While our studies of Europa and Enceladus help us understand icy worlds in general, the ultimate goal is to find similar environments among the exoplanets. The same techniques we use to study moons in our solar system can be adapted to study distant worlds. The physics is the same, only the distance is different. We already have examples of these distant discoveries. Space telescopes like Hubble have already identified water signatures in exoplanet atmospheres. These detections confirm that water is not unique to our solar system. It exists throughout the galaxy, carried in the atmospheres of planets we are only beginning to understand. Each new detection adds to the evidence that water is a common and fundamental component of planetary systems everywhere. Water-rich planets are considered promising candidates for habitability due to potential oceans. The presence of water does not guarantee life, but it creates the conditions in which life, as we understand it, might arise. An ocean provides a medium for chemistry, a place where molecules can mix and combine, where energy flows and gradients exist. These are the conditions that, on Earth, gave rise to the first living things. The migration of planets through their solar systems adds another layer to this story. Planets with abundant water might have been formed farther away and migrated inwards. The water-rich worlds we observe in the habitable zones of their stars may have begun their existence in the cold outer reaches beyond the snowline where ice could form. Over time, gravitational interactions with other planets or their host star may have pushed them inward to their current positions. Understanding water distribution in exoplanets helps refine models of planetary formation. Every detection of water on a distant world is a data point in our understanding of how planets form and evolve. The more we learn, the better we can predict where water-rich worlds might exist, and the more efficiently we can search for them. As you rest here breathing slowly, consider how remarkable it is that we can detect water across such unimaginable distances. Beneath frozen surfaces in the atmospheres of distant planets, in the rings of debris around dying stars, water exists in abundance. We are children of a water world, and our search for water elsewhere is in some sense a search for kinship in the cosmos. The ice moons of our solar system are places of profound silence and beauty. Europa, slightly smaller than our own moon, orbits Jupiter in a realm of intense radiation and gravitational forces. Its surface is a chaos of ice, fractured and refrozen countless times over billions of years. Rust-colored streaks trace the paths of some unknown material welling up from below. Scientists believe these streaks may contain salts from the ocean hidden beneath the ice, clues to the chemistry of an environment we have never directly observed. Enceladus, orbiting Saturn, is even more dramatic in its revelations. This small moon, only about 500 kilometers in diameter, should by all rights be a frozen, dead world. Instead, it is one of the most geologically active bodies in our solar system. The Cassini spacecraft, which orbited Saturn from 2004 until 2017, flew through the plumes erupting from Enceladus's south pole. It detected not just water, but also organic molecules, silica particles, and molecular hydrogen. These ingredients suggest that hydrothermal vents may exist on the ocean floor, similar to the vents that support thriving ecosystems in Earth's deepest oceans. Imagine for a moment the darkness of Enceladus's ocean. No light from the distant sun penetrates the miles of ice above. The water is cold, but not as cold as you might expect. Heat from the moon's interior, generated by tidal forces as Saturn's gravity kneads the rocky core, keeps the water liquid. In this darkness, at hydrothermal vents on the ocean floor, chemical reactions may be occurring right now, reactions that could, perhaps, support a life. Segment 5. The importance of water. We return now to the fundamental question that drives this entire field of research. Why does water matter so much? Why do we search for it so intently, investing billions of dollars and countless hours of human effort? The answer lies in the unique properties of this remarkable molecule and its essential role in the phenomenon we call life. Water detection is essential for understanding the potential for life beyond Earth. Every living thing on our planet depends on water. From the simplest bacteria to the most complex ecosystems, life requires water to exist. Our cells are filled with it. Our biochemistry happens within it. Without water, life as we know it simply cannot function. This is why, when we search for habitable environments beyond Earth, we always begin by searching for water. The search for water involves observing in multiple spectral bands and using advanced algorithms. No single technique is sufficient. Water can hide in many forms, each requiring its own method of detection. Vapor absorbs different wavelengths than ice. Liquid water under an atmosphere looks different from liquid water under a layer of ice. To find water wherever it might exist, we must look in every way we can, using every tool at our disposal. The future holds tremendous promise for these efforts. Future observatories promise to improve water detection sensitivity significantly. Telescopes currently in planning or construction will have capabilities far beyond anything we possess today. They will be able to detect smaller amounts of water on smaller planets, around more distant stars. The discoveries they make will transform our understanding of water in the universe. The observation of water and ice worlds helps us understand the diversity of planetary systems. Our own solar system, with its 4 rocky inner planets and 4 gas giants beyond, is just one example of how a planetary system can be organized. Other systems may be utterly different, with ice giants where we would expect rocky worlds or water-rich planets in places we would never have predicted. Each discovery expands our sense of what is possible. The activity of icy worlds continues to fascinate scientists. water vapor emissions can be linked to geological activity on icy moons. When we detect water vapor coming from a world like Europa or Enceladus, we know that something is happening inside. Heat is being generated, ice is being melted, and water is finding its way to the surface. This activity suggests a dynamic interior, perhaps capable of supporting the chemical processes necessary for life. On moons like Europa, cryovolcanic activity can transport water to the surface. This transport is enormously important for the search for life. If microbes exist in Europa's subsurface ocean, cryovolcanic activity might carry traces of them to the surface, where they could potentially be detected by future spacecraft. The plumes of Enceladus have already been sampled by the Cassini mission, and they were found to contain organic molecules and other interesting chemistry. The detection of water can indicate active processes reshaping icy worlds. A world that shows evidence of ongoing water activity is a world that is still geologically alive. Its interior has not completely frozen solid. Energy is still flowing, heat is still being generated, and the conditions necessary for chemistry and potentially biology are still present. Stagnant, frozen worlds are less promising targets in the search for life. The brightness of icy surfaces provides another way to detect recent activity. High albedo features on icy bodies can suggest recent resurfacing by water or ice. Fresh ice is bright. Ancient ice, battered by cosmic radiation and meteor impacts over millions of years, becomes darker and less reflective. When we observe an icy world with patches of unusual brightness, it may indicate places where fresh ice has recently been deposited. Changes over time can reveal even more. Variations in reflectance spectra over time point to dynamic surface processes. If we observe a world multiple times and see its brightness changing, we know that its surface is being altered. This could be due to cryovolcanism or to other processes we have not yet imagined. These variations transform static observations into windows on geological activity. The tools we use to study ice are becoming increasingly sophisticated. Spectroscopic observations can help identify the presence of solid ice layers. Different types of ice, formed under different conditions, have subtly different spectral signatures. By carefully analyzing these signatures, scientists can determine not just that ice is present, but something about its history and the processes that formed it. Water vapor detection during transits offers clues about atmospheric composition. When a planet transits its star and we detect water vapor in its atmosphere, we learn not just about the water itself, but about the atmosphere as a whole. Is it thick or thin? Does it contain other gases? What temperatures and pressures might exist at the surface? Each piece of information helps us understand whether the planet might be habitable. The challenges we face are significant, but progress continues. Detecting liquid water directly on exoplanets remains technologically challenging, but progress is ongoing. Liquid water does not leave as distinctive a spectral signature as vapor or ice. It cannot be detected through transit spectroscopy in most cases, but scientists are developing new techniques, and the next generation of telescopes may bring this capability within reach. The combination of multiple detection methods enhances confidence in identifying water worlds. No single observation can definitively prove that water exists on a distant world. But when multiple independent methods all point to the same conclusion, our confidence grows. Transit spectroscopy may detect water vapor. Reflectance measurements may suggest ice. Climate models may indicate that liquid water should be stable. Together, these lines of evidence build a compelling case. As you continue to rest, consider how much we have learned about water in the cosmos. It is not rare. It is not confined to Earth. Water exists throughout our galaxy, in forms and places we are only beginning to explore. This knowledge transforms our sense of our place in the universe. We are not unique in possessing this essential ingredient. The cosmos is filled with water, and where water exists, the possibility of life exists as well. Think about the water in your own body for a moment. About 60% of an adult human body is water. This water is not static. It cycles through you constantly, entering as you drink and eat, leaving as you breathe and perspire and eliminate waste. The water molecules that compose you today are not the same molecules that composed you a year ago or 10 years ago. They have cycled through rivers and clouds, through plants and animals, through the great currents of the ocean. Some of these molecules have been on Earth for 4 billion years. Some fell as rain on dinosaurs. Some were breathed by the first humans. And before that, before the water came to Earth, those molecules were in space, in the disk of gas and dust from which our solar system formed. They came from interstellar clouds, from the material ejected by dying stars, from the primordial hydrogen and oxygen that condensed in the first billion years after the Big Bang. The water in your body is ancient beyond comprehension. It connects you to the entire history of the cosmos. This same water, or water very much like it, exists on worlds throughout our galaxy. The search for water on exoplanets is not just a scientific endeavor. It is a profound exploration of our connection to the universe. When we find water on a distant world, we find something of ourselves reflected back across the light years. Segment 6. Subsurface oceans. Beneath the frozen surfaces of icy worlds, oceans may exist in eternal darkness. These hidden seas, warmed by internal heat and protected from the vacuum of space by miles of ice, represent some of the most intriguing environments in the search for life. Tonight, we explore these subsurface realms and consider what they might tell us about water worlds throughout the galaxy. Many future missions aim to explore icy, watery exoplanets in detail. As our technology improves and our understanding deepens, we are designing spacecraft specifically intended to study these hidden oceans. Some may orbit icy moons, mapping their surfaces and measuring their gravitational fields. Others may land and deploy instruments to probe beneath the ice. The future of ocean exploration may lie not in our own seas, but in the hidden waters of other worlds. Ocean worlds like Europa and Enceladus are examples of icy planets with subsurface water. These moons, orbiting in the cold outer reaches of our solar system, have captured the imagination of scientists and dreamers alike. Europa's ocean may contain twice as much water as all of Earth's oceans combined. Enceladus, though smaller, is known to have an ocean feeding its spectacular geysers. Both worlds are priority targets for future exploration. The conditions in these subsurface oceans may be surprisingly hospitable. These moons are thought to harbor conditions suitable for life in their subsurface oceans. Far from the sun, Heated from within by tidal forces and radioactive decay, these oceans may have temperatures and chemistries not unlike Earth's deep sea vents. On Earth, such environments support thriving ecosystems, living entirely without sunlight, drawing energy from chemical reactions between rock and water. The ice that covers these oceans serves multiple purposes. Water ice layers may act as insulators, allowing liquid water beneath to remain stable. Without this insulating layer, the water would quickly freeze or evaporate into space. The ice acts as a blanket, trapping the internal heat and maintaining liquid conditions below. This principle applies not just to the moons of our solar system, but potentially to icy worlds throughout the galaxy. The source of the heat that keeps these oceans liquid is a story of gravitational forces. Tidal forces from parent planets induce geysers and eruptions of water vapor. As Europa orbits Jupiter, the giant planet's gravity stretches and compresses the Moon. This tidal flexing generates heat within Europa's interior, keeping its ocean liquid despite the bitter cold of the outer solar system. The same process operates on Enceladus, where Saturn's gravity drives the Moon's spectacular geysers. These eruptions provide us with remarkable opportunities. These eruptions can be observed remotely, revealing subsurface water. When Enceladus sends its plumes of water ice into space, we can study them from millions of miles away. The Cassini spacecraft flew through these plumes, sampling their contents directly. Future missions may do the same, or may use remote sensing to study plumes from icy exoplanets around other stars. The significance of cryovolcanism cannot be overstated. This cryovolcanic activity is a key feature in the search for habitable worlds. It tells us that liquid water exists. It tells us that heat is being generated. It tells us that materials from the ocean are being transported to the surface. All of these factors are important for the search for life because they suggest dynamic, chemically active environments. The plumes themselves are windows into hidden oceans. Detecting water vapor plumes provides essential clues to subsurface conditions. By analyzing the composition of a plume, scientists can learn about the ocean from which it originates. What salts are dissolved in the water? What organic molecules might be present? What is the temperature and acidity of the ocean? These questions can potentially be answered by studying the vapor that escapes into space. The implications for life are profound. Subsurface lakes or oceans could provide habitats for microbes. On Earth, life exists in the deepest, darkest environments, wherever liquid water and chemical energy are available. There is no reason to think that similar environments on other worlds would be sterile. The oceans of Europa and Enceladus, and perhaps of countless icy exoplanets, may harbor life that has evolved entirely independently from Earth's. The chemistry of cryovolcanic eruptions adds another dimension. Cryovolcanic eruptions can also deposit salts and other chemicals helpful for life. The plumes of Enceladus contain not just water, but sodium chloride, silica, and organic compounds. These materials suggest that the ocean beneath the ice is interacting with rock, creating the kind of chemical gradients that can power life. Similar processes may occur on water worlds throughout the galaxy. The missions being planned will take us closer to answers. Future missions aim to analyze these plumes directly. NASA's Europa Clipper, scheduled to launch in the coming years, will make dozens of close flybys of Europa, studying its ice shell and searching for evidence of plumes. If plumes are found, future missions may be designed to fly through them, sampling their contents for signs of life. The search has never been more exciting. As you rest, let these hidden oceans fill your imagination. Picture vast spaces of liquid water, dark and still, far beneath a ceiling of ice. Imagine whatever might swim or drift in those waters, evolved over billions of years in conditions utterly unlike anything on Earth. These possibilities are not merely science fiction. They are scientific hypotheses, testable and potentially verifiable within our lifetimes. The age of ocean exploration may be just beginning, not ending. Consider the profound darkness of a subsurface ocean. On Earth, our deepest oceans are dark, but they receive a trickle of organic matter from the sunlit surface above. On Europa or Enceladus, no such connection exists. The ocean is sealed off, a world unto itself. Any life that exists there would have evolved independently, shaped by conditions we can only imagine. It might be utterly alien, using biochemistry we have never encountered. Or it might be surprisingly similar to life on Earth, suggesting that the fundamental chemistry of life is universal. The thought of such life fills scientists with a mixture of excitement and humility. If we find life on Europa, or Enceladus, or some distant exoplanet, it will answer one of humanity's oldest questions: are we alone? And yet the answer might raise even more questions. How did life arise on that world? When did it appear? How has it evolved? Is it intelligent? Does it wonder, as we do, about life elsewhere in the cosmos? These questions drift through the darkness like fish through an alien sea. We do not yet know the answers, but the search for them drives us forward. Every observation, every mission, every analysis brings us closer to understanding the nature of life in the universe. Segment 7. The habitable zone. There is a region around every star where conditions might be just right for liquid water to exist on a planet's surface. Not too hot, not too cold. This zone has been called the habitable zone, or sometimes more poetically, the Goldilocks zone. Understanding this concept is central to the search for life-bearing worlds. The search for water worlds extends to exoplanets orbiting distant stars. Our own solar system contains one planet in the habitable zone, Earth. But every star has its own habitable zone, and around many of those stars, planets are orbiting. Some of those planets may lie within their star's habitable zone. Some of them may have liquid water on their surfaces. The statistics suggest that billions of such worlds may exist in our galaxy alone. Many of these planets are located in the habitable zone where liquid water could exist. The boundaries of the habitable zone depend on the star's temperature and brightness. Around a cool, dim red dwarf star, the habitable zone is very close to the star. Around a hot, bright blue star, it extends much farther out. In each case, the principle is the same. We are looking for the range of distances where water can remain liquid on a planet's surface. Detection of water on exoplanets often involves analyzing starlight passing through their atmospheres. This is the technique of transit spectroscopy we discussed earlier. When a planet passes in front of its star, some of the starlight filters through the planet's atmosphere. By analyzing which wavelengths are absorbed, we can determine what gases are present. If water vapor is detected in the atmosphere of a planet in the habitable zone, the possibility of liquid water on the surface becomes much more likely. Water signatures can include absorption lines of water vapor in the infrared. The infrared portion of the spectrum is particularly useful for detecting water. At these wavelengths, water molecules absorb light strongly at specific frequencies, creating distinctive dips in the spectrum. These absorption lines are like fingerprints, uniquely identifying the presence of water even from enormous distances. Clouds of water vapor can obscure some signals, complicating detection. On Earth, our atmosphere contains both water vapor and water clouds. Clouds can make it harder to see through to the surface below. The same is true for exoplanets. A world with thick clouds might hide its surface water from our view. Paradoxically, the very thing we are searching for can sometimes make our search more difficult. The presence of surface water would greatly increase a planet's habitability potential. A planet with liquid water on its surface has met one of the most important conditions for life. Water provides a medium for chemistry, a solvent in which complex molecules can form and interact. It moderates temperature, stores and releases heat, and cycles through ecosystems. Surface water transforms a barren rock into a potentially living world. Long-term stability matters as well. Planets with stable, long-lasting oceans could be promising targets in the search for life. Life on Earth took billions of years to evolve from simple cells to complex organisms. If a planet's oceans are unstable, evaporating away or freezing solid over short time scales, complex life may never have a chance to emerge. The most promising targets are worlds where conditions have remained stable for eons. The discovery of water on small rocky planets boosts the possibility of habitability. For many years, most known exoplanets were gas giants, worlds too massive and too gaseous to support life as we know it. But increasingly, we are discovering smaller, rocky planets more similar to Earth. When water is detected on such a world, and when it orbits within the habitable zone, the implications are profound. Water-rich planets may also have thick atmospheres that help maintain liquid water. An atmosphere acts as a blanket, trapping heat and regulating temperature. A thick atmosphere rich in greenhouse gases can keep a planet warm even at distances from its star where bare rock would freeze. Water vapor itself is a greenhouse gas, so a water-rich atmosphere can create conditions favorable for liquid water on the surface. The number of known water worlds continues to grow. As detection techniques improve, the number of known water worlds is expected to grow. Every year brings new discoveries. Telescopes become more sensitive, analysis methods become more sophisticated, and the catalogue of potentially habitable worlds expands. We are living through a golden age of exoplanet discovery, and water is one of the main things we are finding. Understanding the distribution of water in the cosmos helps scientists understand planetary evolution. Where does water come from? How does it end up on planets in the habitable zone? These questions connect to broader questions about how planetary systems form and evolve. By studying water throughout the galaxy, we learn not just about individual worlds, but about the cosmic processes that create them. Tonight, as you drift towards sleep, consider your own place in this cosmic story. You live on a water world, a planet where liquid water has existed continuously for billions of years. This is rare and precious. And yet, the evidence suggests that other such worlds exist, perhaps in abundance, scattered throughout the galaxy. You are not alone in this universe of water and ice. Somewhere out there, other oceans may be catching starlight. Other shores may be waiting to be discovered. The concept of the habitable zone is beautifully simple, yet endlessly complex in its implications. The basic idea is straightforward. Too close to a star and water boils away. Too far and it freezes solid. But the reality is far more nuanced. The type of star matters. The composition of the planet's atmosphere matters. The presence of greenhouse gases, the reflectivity of the surface, the tilt of the planet's axis, the activity of its geology, all play a role in determining whether water can remain liquid. On Earth, we exist at a particular point in this complex interplay of factors. Our Sun provides just the right amount of energy. Our atmosphere contains just the right mix of gases. Our planet has just the right amount of water. We are, in a sense, balanced on a knife's edge, and we have been for 4 billion years. This long stability has allowed life to evolve from simple cells to the incredible diversity we see today. Other worlds, in other star systems, may have found similar balances. Some may be warmer than Earth, with more water vapor in their atmospheres. Others may be cooler, with vast ice caps covering much of their surfaces. Some may have no land at all, just endless oceans stretching from pole to pole. Each represents a different solution to the puzzle of habitability, a different way of maintaining liquid water over geological time. Segment 8. Ice layers and hidden oceans. The structure of icy worlds is more complex than simple frozen spheres. Beneath their surfaces, layers of ice and water can form intricate arrangements, with oceans sandwiched between shells of ice at different pressures and temperatures. These hidden layers may hold the key to understanding where life might exist. Some worlds may have high-pressure ice layers beneath their surfaces, separated from liquid oceans. Water ice has many forms, depending on temperature and pressure. At very high pressures, ice forms crystalline structures different from ordinary ice. On large icy worlds, the weight of ice above can compress lower layers into these exotic forms. This means that an ocean of liquid water might be sandwiched between ordinary surface ice and high-pressure ice below. These ice layers can act as barriers, isolating the ocean below from the atmosphere. If an ocean is completely enclosed by ice above and below, it exists in isolation from the rest of the planet. Gases cannot exchange with the atmosphere. Light cannot penetrate from above. Any life in such an ocean would evolve in conditions utterly unlike anything on Earth's surface. Understanding these barriers helps us predict what conditions might exist in hidden oceans. The surfaces of icy moons are not static. On some icy moons, surface ice is continually renewed by cryovolcanic activity. The ice that covers Europa and Enceladus is not billions of years old. It is being constantly refreshed by material welling up from below. Old ice is broken up and recycled, new ice is deposited, and the surface remains relatively young and fresh. This activity is evidence of the dynamic processes occurring within. The composition of ice can tell us about what lies beneath. The composition of icy shells helps determine the likelihood of life in the oceans below. Is the ice pure water ice, or does it contain salts and other compounds? Are there organic molecules frozen within it? By studying the ice, we can learn about the ocean from which it came. Future landers on Europa or Enceladus may sample surface ice, searching for chemical signatures of life in the ocean below. By studying ice and water signatures, scientists infer the potential for habitable environments. Every piece of data adds to the picture. The thickness of ice, its composition, its age, its temperature, all provide clues. Combined with information about heat sources and chemical processes, these clues help scientists assess whether a given world might support life. The search is like detective work, piecing together evidence from millions of miles away. Observations suggest some planets may have warm, water-rich surface conditions. Not all water worlds are frozen. Some exoplanets may have temperatures warm enough for liquid water to exist openly on their surfaces. These would be ocean worlds in the most direct sense, planets where seas stretch from horizon to horizon under alien suns. Such worlds would be tremendously exciting targets in the search for life. The detection of water in exoplanets often relies on modeling and spectral analysis. We cannot see these distant surfaces directly. Instead, we must infer their nature from the light that reaches us. Computer models help us understand what different kinds of surfaces and atmospheres would look like. By comparing our observations to these models, we can narrow down the possibilities and make educated guesses about surface conditions. Future capabilities will allow even finer distinctions. Future telescopes will be more capable of distinguishing fresh water from salty oceans. On Earth, we can taste the difference between fresh and salt water. In space, we must rely on spectral signatures. Salt affects how water interacts with light, and these effects can be detected with sufficiently sensitive instruments. Future telescopes may be able to tell us not just that water exists on a distant world, but what kind of water it is. The variety of water worlds is extraordinary. Water worlds are among the most intriguing targets in cosmic exploration. Some may be covered entirely in ice. Others may have ice caps and open oceans like Earth. Still others may be ocean worlds with no solid surface at all, water hundreds of miles deep over a core of rock or high-pressure ice. Each type presents different possibilities for habitability and different challenges for detection and study. The significance of water in the cosmic story of life cannot be overstated. Water and ice play a central role in astrobiology and understanding life's potential. Astrobiology is the study of life in the universe, including its origins, evolution, distribution, and future. At every turn, water appears as a key factor. Where we find water, we find the possibility of life. Where water is absent, life as we know it cannot exist. Rest now and let these layers of ice and water settle in your mind like sediment drifting to an ocean floor. The universe is filled with water, hidden in places we are only beginning to explore. Beneath frozen surfaces, in the atmospheres of distant planets, in the rings of debris around dying stars, water exists in abundance. We are children of a water world, and our search for water elsewhere is, in some sense, a search for kinship in the cosmos. The structure of icy worlds challenges our intuition. On Earth, ice floats on water, a property that seems natural to us but is actually quite unusual among substances. This happens because water expands slightly when it freezes. making ice less dense than liquid water. This quirk of physics has profound implications. It means that lakes and oceans freeze from the top down, leaving liquid water beneath where life can survive the winter. On high-pressure worlds, water behaves differently. At extreme pressures, ice can form in crystalline structures that are denser than liquid water. This hot ice, as it is sometimes called, can exist at temperatures well above what we normally associate with freezing. A world with enough water might have layers upon layers of different ice types, separated by oceans of liquid water at different depths. The structure would be unlike anything on Earth, a layered world of water in all its phases. Such worlds may be common in the galaxy. Many exoplanets are larger than Earth, with masses several times greater. If these super-Earths contain significant amounts of water, the pressures in their interiors would be enormous, creating exactly the conditions needed for these exotic ice structures. The oceans sandwiched between ice layers would be unlike any ocean we know, isolated from the atmosphere above and the rock below, yet potentially habitable in their own strange way. Segment 9. Detection methods and challenges. The search for water on distant worlds pushes the limits of our technology and ingenuity. Every detection method has its strengths and limitations, its optimal conditions and blind spots. Tonight, we examine these methods more closely, understanding both what they can tell us and what challenges remain. The presence of water is considered a key indicator of possible habitability. This principle guides our entire search strategy. We do not yet have the ability to detect life directly on exoplanets, but we can detect water, and water is a prerequisite for life as we understand it. By finding water, we identify the most promising places to look for life when our technology becomes more capable. Detection of water vapor is often the first clue researchers seek on new exoplanets. Water vapor is relatively easy to detect through transit spectroscopy. Its absorption features are strong and distinctive. When a new exoplanet is discovered, one of the first questions scientists ask is whether water vapor is present in its atmosphere. This single piece of information can transform our understanding of the planet's potential. Direct imaging poses significant challenges, but also offers unique rewards. Direct imaging challenges motivate spectral and indirect detection methods. To image a planet directly, we must separate its faint light from the overwhelming glare of its host star. This is like trying to see a firefly next to a searchlight from miles away. The challenge has driven the development of sophisticated coronagraphs, starshades, and other technologies that block or suppress starlight while allowing planetary light through. The diversity of worlds we are discovering is remarkable. The diverse worlds in our galaxy hint at a rich variety of environments. Some exoplanets are hot Jupiters, gas giants that orbit impossibly close to their stars. Others are super-Earths, rocky worlds larger than our planet but smaller than Neptune. Still others are ice giants, water worlds, or planets with no analogue in our solar system. Each type challenges our understanding and expands our sense of what is possible. Some water worlds may offer protection for life in unexpected places. Water-rich planets may host life in subsurface oceans shielded from harsh surface conditions. On some worlds, the surface may be bombarded by radiation, sterilized by extreme temperatures, or stripped by powerful stellar winds. And yet, beneath the ice, in hidden oceans, conditions may be benign enough for life to flourish. The surface tells only part of the story. Our own solar system provides a laboratory for understanding distant worlds. Studying icy planets in our solar system provides clues to distant water worlds. Europa, Enceladus, Titan, and other icy moons are close enough to study in detail. What we learn about these worlds helps us interpret the faint signals we receive from exoplanets light years away. The nearby worlds are our training ground for the distant frontier. Future missions will bring us closer than ever to these hidden oceans. Future exploration missions aim to sample cryovolcanic plumes directly. A spacecraft flying through a plume could analyze its contents in real time, searching for organic molecules, cell-like structures, or other signatures of life. This is not science fiction. Missions to do exactly this are being planned and funded. Within the coming decades, we may have direct samples from an extraterrestrial ocean. The quest for water drives our ongoing exploration. The quest to understand water in space continues to inspire curiosity and discovery. Each generation builds on the discoveries of the last. The astronomers who first detected exoplanets could not have imagined the water world discoveries we make today. And we cannot imagine what discoveries await the astronomers of tomorrow. The quest continues, driven by curiosity, enabled by technology, and guided by the presence of water. Water ice on exoplanets can be detected through its unique infrared signature. This bears repeating because it is so fundamental to our search. Ice absorbs and reflects infrared light in distinctive ways. By measuring infrared emissions and reflectance, we can detect ice on worlds we will never visit. This capability allows us to survey thousands of distant worlds, searching for the telltale signatures of frozen water. Spectral analysis reveals the presence of water vapor in exoplanet atmospheres. Through careful measurement of starlight passing through planetary atmospheres, we can identify the molecular fingerprints of water vapor. This technique has already confirmed water vapor on multiple exoplanets, and the list continues to grow. Each detection adds to our catalogue of water worlds and refines our understanding of where water exists. Water vapor can be produced by cryovolcanic eruptions on icy worlds. When we detect water vapor in the atmosphere of a cold, icy world, it may indicate active cryovolcanism. The water is being erupted from the interior, adding to the atmosphere temporarily before freezing out or escaping to space. This variability can help us identify which worlds are geologically active and therefore potentially habitable. As you continue to rest, consider the patience required for this search. Astronomers may observe a single exoplanet for years, gathering data one transit at a time, building up enough signal to detect water vapor or other molecules. The work is slow, methodical, and painstaking, but the rewards are extraordinary. The knowledge that we are not alone in possessing this essential ingredient for life. The challenges of detection are immense, and yet we continue to make progress. Consider what we are attempting. We are trying to detect water on worlds that are so far away that even light, the fastest thing in the universe takes years to reach us from there. We are trying to identify a specific molecule in an atmosphere we cannot see, orbiting a star that outshines it by billions to one. We are trying to infer the presence of oceans on surfaces we cannot resolve, around stars that appear as nothing more than points of light. And yet, we succeed. Through ingenuity and persistence, through the accumulated wisdom of generations of scientists, we have developed techniques that can do exactly these seemingly impossible things. Transit spectroscopy, direct imaging, radial velocity measurements, gravitational microlensing. Each technique contributes a piece of the puzzle. Together, they allow us to characterize worlds we will never visit, to understand environments we will never directly experience. This is one of the great achievements of human civilization. We have extended our senses so far beyond their natural limits that we can now probe the atmospheres of planets orbiting other stars. We have built instruments so sensitive that they can detect the tiny wobble of a star caused by an orbiting planet. We have created algorithms so sophisticated that they can tease out the faint signature of water vapor from the overwhelming noise of stellar light. These are triumphs of the human spirit, testaments to what we can accomplish when we work together toward a common goal. Segment 10: Albedo and Surface Features. The brightness of a world can reveal secrets about its surface. How much light a planet reflects and at what wavelengths provides clues about what materials cover its surface. Ice, water, rock, and vegetation all have distinctive reflective properties. And by studying a planet's brightness, we can begin to map its surface from light years away. Ice-rich exoplanets may have high albedo surfaces due to reflective ice layers. Albedo, as we have discussed, measures how much light a surface reflects. Fresh ice, especially snow, has one of the highest albedos of any natural material. A planet covered in ice would be very bright, reflecting a large fraction of the starlight that falls on it. This brightness can be detected even from enormous distances. Reflectance changes over time can indicate resurfacing by water or ice. If an icy world's brightness changes over time, it may indicate that the surface is being renewed. Fresh ice deposited by cryovolcanic activity would be brighter than older weathered ice. By monitoring a world's brightness over months or years, we can detect these changes and infer the geological processes occurring on the surface. Transmission spectroscopy during transits helps identify water vapor in atmospheres. This technique, which we have explored throughout our journey, remains one of the most powerful tools for detecting water. When a planet passes in front of its star, the atmosphere filters starlight in characteristic ways. Water vapor, with its distinctive absorption features, can be identified in this filtered light. Gas absorption features during transits provide clues about water-rich atmospheres. Besides water vapor, other gases may be present that tell us about a world's water content. Carbon dioxide, oxygen, and other molecules can all be detected through transit spectroscopy, and their presence or absence helps us understand the overall composition and chemistry of the atmosphere. High H2O. Column densities during eruptions suggest active cryovolcanism. When we observe an icy world and detect unusually high concentrations of water vapor, it may indicate an ongoing eruption. These measurements, made over time, can reveal the frequency and intensity of cryovolcanic activity, helping us understand the internal dynamics of icy worlds. Direct imaging reveals spectra of surface oceans on distant worlds. As direct imaging technology improves, we may be able to capture light reflected from the surfaces of exoplanets. The spectra of this reflected light can tell us about surface conditions. Liquid water has a distinctive spectrum, and detecting it would be strong evidence for surface oceans. Indirect methods include anomalously high reflectivity. Sometimes the clues are subtle. A world that is brighter than expected might have fresh ice on its surface. A world that varies in brightness might have changing cloud cover or seasonal ice caps. These indirect indicators help us narrow down which worlds are most likely to have water. Cloudy, water-rich atmospheres produce specific spectral features. Clouds of water droplets or ice crystals scatter and absorb light in characteristic ways. By studying these features, we can learn not just that water is present, but how much water is present and in what form. A planet with thick water clouds would look different from one with a clear, dry atmosphere. Water-rich exoplanets are prime for habitability studies. Every detection of water on an exoplanet adds that world to the list of priority targets. These are the worlds that will receive the most attention from future telescopes. These are the worlds that may one day reveal the first signs of life beyond Earth. Water vapor plumes help infer subsurface oceans. The connection between surface activity and subsurface conditions is crucial. When we detect plumes of water vapor erupting from an icy world, we know that liquid water exists somewhere beneath the surface. This water may be in contact with rock, creating the chemical conditions necessary for life. The plumes are windows into hidden oceans. As you rest here, imagine looking down on an icy world from space. Its surface gleams white with fresh ice, cracked by dark lines where geological forces have fractured the shell. Here and there, plumes of vapor rise, catching sunlight and glittering like diamonds. Beneath that ice, vast dark oceans may stretch for thousands of miles. This is not fantasy. This is the reality of worlds like Europa and Enceladus, and perhaps countless exoplanets throughout the galaxy. The study of albedo connects us to our earliest observations of other worlds. Before we had spacecraft, before we had spectroscopy, we could still measure how bright planets and moons appeared. Mars with its rusty hue, Venus with its brilliant white clouds, our own moon with its patches of light and dark. These variations in brightness told us that the surfaces of these worlds were not uniform, that different materials reflected light in different ways. Now we apply the same principles to exoplanets. A world covered in ice would be very bright, reflecting most of the light that falls on it. A world covered in dark ocean would be dimmer, absorbing much of the incoming light. A world with patchy clouds would vary in brightness as it rotated, the clouds moving in and out of view. By measuring these variations, we can learn about surface conditions on worlds we cannot see directly. The ice caps of Earth are visible from space as bright patches near the poles. If an alien astronomer were observing our planet, they would notice these bright regions and might correctly infer that they are covered in ice. They might also notice that the brightness of the poles changes with the seasons as ice advances and retreats. This seasonal variation is another clue to the nature of a planet, a hint that dynamic processes are at work on its surface. Segment 11. Geological activity. The search for life is intimately connected to the search for geological activity. A world that is geologically active has energy flowing through it, heat being generated, materials being cycled and recycled. These are the conditions that can sustain complex chemistry, including the chemistry of life. Tonight, we explore the connections between geological activity and water. Water vapor emissions indicate geological activity on icy moons. When we detect water vapor coming from an icy world, we know that something is happening beneath the surface. The ice is being heated, melted, and ejected. This requires energy, and energy implies geological activity. The vapor is a beacon, signaling that this is a dynamic, active world. Cryovolcanic eruptions transport water to the surface of icy moons. The process of cryovolcanism moves material from the interior to the surface. On Earth, volcanoes bring rock and gases from deep within the planet. On icy moons, cryovolcanoes bring water and ice. This transport is enormously important because it creates a connection between the surface, which we can observe, and the interior, which we cannot. High albedo features suggest recent resurfacing by water or ice. When we observe bright patches on an icy moon, we know that fresh material has been deposited recently. The brightness of these features is a clock, telling us how recently geological activity has occurred. Worlds with bright, fresh surfaces are geologically active worlds. Spectroscopic observations identify solid ice layers on icy worlds. By analyzing the spectra of reflected light, we can determine not just that ice is present, but what kind of ice it is. Different crystal structures produce different spectra. Ice that has been recently deposited looks different from ice that has been exposed to radiation for millions of years. These details help us understand the geological history of icy worlds. Water vapor detection reveals atmospheric composition during transits. Every transit observation teaches us something about the atmosphere of the planet crossing in front of its star. Water vapor is often one of the first things we search for, but we also look for other gases that might indicate geological activity. Volcanic gases, sulfur compounds, and other molecules can all provide clues. Direct detection of liquid water is advancing. The technology to detect liquid water directly on exoplanets is still in development, but progress is being made. Future telescopes with extreme precision may be able to detect the distinctive spectra of liquid water on planetary surfaces. This would be a breakthrough, allowing us to identify ocean worlds with confidence. Multiple methods increase confidence in water detection. No single observation is definitive, but when multiple independent methods all point to the same conclusion, our confidence grows. If transit spectroscopy detects water vapor and reflectance measurements suggest ice and climate models indicate stable liquid water, we can be reasonably confident that we are looking at a water world. Future missions will explore icy, watery exoplanets in greater detail. The telescopes and spacecraft being planned today will have capabilities far beyond anything we currently possess. They will be able to study exoplanets in unprecedented detail, detecting water and other molecules with greater precision, mapping surfaces and atmospheres, and searching for signs of life. The future is bright with possibility. Ocean worlds like Europa and Enceladus are analogues for icy exoplanets. These nearby worlds help us understand what we might find among the stars. By studying Europa and Enceladus up close, we learn what icy ocean worlds look like, how they behave, and what signatures they produce. This knowledge prepares us for the discoveries we will make when we turn our attention to exoplanets. Subsurface oceans on icy moons may harbor microbial life. This is perhaps the most exciting possibility of all. In the dark oceans beneath miles of ice, life may have arisen independently from Earth. If we find it, it will transform our understanding of biology, of evolution, and of our place in the universe. The search for life in subsurface oceans is one of the great scientific quests of our time. As you continue to rest, let these possibilities settle into your consciousness. We live at a remarkable moment in human history, when the discovery of life beyond Earth has become a realistic possibility within our lifetimes. The water we search for is the same water that makes up most of your own body. In searching for water elsewhere, we are, in some sense, searching for reflections of ourselves. Geological activity is, in a profound sense, the heartbeat of a world. A geologically dead planet is a world that has grown cold, whose interior has frozen solid, whose surface is unchanging. Such worlds may still be beautiful, but they lack the dynamism that we associate with living systems. A geologically active world, by contrast, is a world in motion. Heat flows from its interior. Materials cycle between surface and depths. The surface evolves over time, erasing old features and creating new ones. This activity requires energy, and energy is one of the key ingredients for life. On Earth, geothermal energy supports thriving ecosystems at hydrothermal vents in the deep ocean. Bacteria and archaea harvest chemical energy from the interaction of hot water and rock. Animals feed on these microbes, building food webs that exist entirely without sunlight. Similar ecosystems may exist on other worlds wherever water meets heat and rock. The detection of geological activity on an exoplanet would be tremendously exciting. It would tell us that the planet is not a dead, frozen ball, but a dynamic world where interesting chemistry might be occurring. Combined with the detection of water, it would make the planet a prime target in the search for life. We would focus our best instruments on it, searching for any sign of biology in its atmosphere or on its surface. Segment 12. Insulation and stability. The persistence of liquid water depends on protection from the harsh conditions of space. Ice layers, atmospheres, and other insulating features can shield water from evaporation, freezing, and radiation. Understanding these protective mechanisms helps us identify which worlds might harbor stable, long-lasting bodies of water. Water ice layers can insulate subsurface oceans, keeping them stable. On worlds like Europa and Enceladus, the ice shell acts as a blanket, preventing the ocean below from freezing solid or boiling away into space. This insulation allows liquid water to persist for billions of years, providing ample time for complex chemistry and potentially life to develop. Tidal forces from parent planets can induce geysers and eruptions. The heat that keeps these oceans liquid comes from tidal flexing. As a moon orbits its parent planet, gravitational forces stretch and compress its interior. This mechanical energy is converted to heat, maintaining liquid conditions despite the bitter cold of the outer solar system. Without this tidal heating, the oceans would freeze solid. Eruptions can be observed remotely, revealing subsurface water. The geysers of Enceladus are visible from millions of miles away. They send plumes of ice crystals high above the moon's surface, where they catch sunlight and become visible. These eruptions confirm the existence of liquid water below and provide opportunities for study by passing spacecraft. Cryovolcanic activity is key in habitability studies. When assessing whether a world might be habitable, geologists and astrobiologists pay close attention to signs of cryovolcanism. This activity indicates that liquid water exists, that heat is being generated, and that materials are being cycled between the interior and surface. All of these factors contribute to habitability. Plumes may contain salts and chemicals helpful for life. The plumes of Enceladus have been analyzed by the Cassini spacecraft, and they contain a variety of interesting compounds. Sodium chloride, silica particles, and organic molecules have all been detected. These materials suggest a complex, chemically rich environment in the ocean below. Future missions will sample plumes directly. Building on the success of Cassini, future missions are being designed to fly through plumes and analyze their contents in detail. Advanced instruments will search for amino acids, lipids, and other molecules associated with life. If life exists in these subsurface oceans, its chemical traces may be present in the plumes. Water worlds beyond our solar system are promising targets. The lessons we learned from Europa and Enceladus apply to exoplanets as well. Icy worlds with internal heat sources may exist throughout the galaxy, each potentially harboring a subsurface ocean. These worlds are promising targets in the search for life, and they are high priorities for future telescopes. Many exoplanets are in the habitable zone where liquid water could exist. The habitable zone concept applies to surface water, but subsurface oceans can exist far beyond this zone. A world too cold for liquid water on its surface might still harbor an ocean beneath its ice. This expands the range of potentially habitable environments enormously. Analyzing starlight through exoplanet atmospheres reveals water signatures. Every transit observation provides new information. As starlight passes through an atmosphere, it picks up the chemical fingerprints of the gases present. Water vapor, with its distinctive absorption features, can be detected in this way, adding another piece to the puzzle of planetary composition. Water vapor absorption lines in the infrared indicate water presence. The infrared region of the spectrum is particularly rich in water absorption features. Multiple lines at different wavelengths combine to create a distinctive pattern that can be recognized even in noisy data. Detecting this pattern is one of the main goals of transit spectroscopy. As you rest here, breathing slowly and deeply, consider the remarkable stability that water can achieve under the right conditions. Oceans that have persisted for billions of years, hidden beneath shells of ice, warmed by the gentle flexing of their moon's interiors. These are patient oceans existing on timescales that dwarf human history. If life has arisen in these waters, it has had eons to evolve and adapt. What forms might it have taken? What mysteries await discovery? These questions drift through the cosmos, unanswered for now, but perhaps not forever. Stability is a gift that not all worlds possess. On some planets, conditions may change too rapidly for complex life to evolve. Ice ages may come and go in geologically brief intervals. Oceans may evaporate, then reform, then evaporate again. The chemistry of the atmosphere may shift dramatically as volcanic eruptions add gases or impacts strip them away. In such unstable environments, life might arise only to be extinguished before it can evolve beyond simple forms. Earth has been fortunate in its stability. Our planet has maintained liquid water on its surface for nearly 4 billion years, an almost unimaginable span of time. During this period, life evolved from simple cells to the incredible diversity we see today. It survived mass extinctions, ice ages, and continental rearrangements. The stability of Earth's environment, maintained by complex feedback loops involving the atmosphere, the oceans, and the biosphere itself, has been crucial to this long evolutionary journey. When we search for habitable worlds beyond Earth, we are not just looking for water, we are looking for stability. We are looking for worlds where conditions have remained favorable long enough for life to arise and evolve. These are the worlds most likely to harbor complex ecosystems, perhaps even intelligent beings looking back at us across the void. Segment 13. Clouds and atmospheres. The atmospheres of water-rich worlds present both opportunities and challenges. Clouds can scatter light in ways that reveal their presence, but they can also obscure the surface below. Understanding atmospheric water is crucial for assessing the habitability of distant planets. Clouds of water vapor can complicate detection, but provide clues to habitability. On Earth, clouds cover about 2/3 of the planet at any given time. They are a visible sign of our abundant water. On exoplanets, clouds can hide surface features from view, but their very presence indicates that water exists. The detection of clouds is thus both a challenge and an opportunity. Surface water greatly increases habitability potential. A planet with liquid water on its surface has met one of the most important conditions for life. Surface water allows for photosynthesis, for diverse ecosystems, for the kind of complex biosphere that has evolved on Earth. While subsurface oceans are promising, surface water remains the gold standard in the search for habitable worlds. Planets with stable oceans are promising for life. Stability matters enormously. Life needs time to evolve, and evolution requires consistent conditions over long periods. A planet where oceans come and go, where water freezes and thaws on short timescales, may never develop complex life. The most promising targets are worlds where oceans have persisted for billions of years. Water-rich planets may have thick atmospheres maintaining liquid water. The atmosphere and the ocean work together. A thick atmosphere traps heat, preventing water from freezing. Water vapor in the atmosphere adds to this greenhouse effect. The interplay between atmosphere and ocean determines the climate of a water world. Improved detection techniques will reveal more water worlds. Every advance in telescope technology reveals more about the planets we observe. As instruments become more sensitive, we can detect smaller amounts of water on smaller planets around more distant stars. The catalogue of known water worlds grows with each passing year. Water distribution in the cosmos informs planetary evolution. By studying where water exists in different planetary systems, we learn about how those systems formed and evolved. Water is not distributed randomly. It reflects the history of a planetary system, the processes of condensation and migration, the delivery of comets and asteroids. Understanding this distribution is key to understanding planetary science. High-pressure ice layers may separate oceans from the surface. On some water worlds, the pressure at depth may be so great that water crystallizes into exotic forms of ice. These high-pressure ice layers can create barriers between the ocean and the rocky core below. Understanding this structure helps us assess whether geochemical processes can occur that might support life. Ice layers can act as barriers, isolating subsurface oceans. The ice above and the high-pressure ice below can completely enclose an ocean, cutting it off from the atmosphere and the rocky interior. Such an isolated ocean might still support life if it has sufficient heat and nutrients, but it presents unique challenges for detection and study. Surface ice is renewed by cryovolcanic activity on some moons. The surfaces of Europa and Enceladus are geologically young, renewed by material from below. This renewal erases craters and other features, keeping the surface fresh and bright. It is evidence of ongoing activity, of oceans that continue to interact with their icy shells. Ice shell composition affects the likelihood of life. The ice that covers the subsurface ocean is not necessarily pure water ice. It may contain salts, organic compounds, and other materials. The composition of this ice affects how easily materials can exchange between the ocean and the surface, which in turn affects the likelihood that life could arise and persist. As you continue to rest, imagine floating in the clouds of a distant water world. Water droplets surround you, scattering light into soft halos around an unfamiliar sun. Below, glimpsed through breaks in the clouds, an ocean stretches to the horizon. This world is not Earth, but it is not entirely alien either. Water, in all its forms, creates environments that have much in common with our own. The chemistry of water, its unique properties, shape worlds throughout the galaxy in ways both familiar and strange. Clouds are both a challenge and an opportunity for exoplanet scientists. They obscure the surface below, making it harder to determine surface conditions. But they also scatter and reflect light in characteristic ways, allowing their composition to be determined from afar. A world with thick water clouds would look different from one with ammonia clouds or sulfuric acid clouds. By analyzing the light scattered by clouds, we can learn about atmospheric composition and, by extension, about the conditions that might exist on the surface below. On Earth, clouds are constantly forming and dissipating, driven by the endless cycle of evaporation and condensation. Water evaporates from the oceans, rises into the atmosphere, condenses into clouds, and falls back as rain or snow. This water cycle is one of the most fundamental processes on our planet, responsible for weather patterns, for the distribution of fresh water, for the erosion of mountains, and the deposition of sediments. A similar cycle may operate on other water worlds, each with its own unique characteristics. Some exoplanets may have clouds unlike anything on Earth. Worlds close to their stars might have clouds of molten rock, droplets of liquid iron condensing in the atmosphere. Worlds far from their stars might have clouds of frozen carbon dioxide or nitrogen. Each type of cloud has its own spectral signature, its own way of interacting with light. By detecting these signatures, we can learn about the incredible diversity of atmospheric conditions throughout the galaxy. Segment 14: Observations and Evidence. The evidence for water on exoplanets comes from many sources. Each observation adds to the growing body of knowledge, building a picture of water distribution throughout the galaxy. Tonight we survey some of the key observations that have shaped our understanding. Observations suggest some planets have warm, water-rich surfaces. Not all water worlds are frozen. Some exoplanets orbit at distances where liquid water could be stable on the surface. These warm water worlds are particularly intriguing because they may support the kind of diverse, surface-based ecosystems that we see on Earth. Spectral analysis and modeling help identify water worlds. The data we collect from telescopes must be carefully analyzed and interpreted. Computer models simulate what different kinds of planets would look like, and by comparing observations to these models, we can determine the most likely conditions on distant worlds. This combination of observation and modeling is fundamental to exoplanet science. Future telescopes will distinguish freshwater from salty oceans. On Earth, freshwater and saltwater have different properties. Salt affects how water freezes, how it interacts with light, and how it behaves chemically. Future telescopes with extreme precision may be able to detect these differences on exoplanets, telling us not just that water exists, but what kind of water it is. Water worlds are among the most intriguing cosmic targets. Among all the types of exoplanets we have discovered, water worlds hold a special fascination. They are the most likely to support life as we know it. They are the most similar to our own Earth. They represent perhaps the best chance we have of finding kinship in the cosmos. Water and ice play a central role in astrobiology. The science of astrobiology seeks to understand life in the universe, its origins, its distribution, its future. At every step, water plays a central role. It is the medium in which life arose on Earth, and it is likely the medium in which life would arise elsewhere. Understanding water is essential to understanding life. Water is a key indicator of possible habitability. When we assess whether an exoplanet might be habitable, one of the first questions we ask is whether water is present. Its presence does not guarantee life, but its absence makes life as we know it impossible. Water is a prerequisite, a necessary condition, a starting point for the search for life. Water vapor is often the first clue sought on new exoplanets. Transit spectroscopy allows us to detect water vapor relatively easily. Its strong absorption features make it stand out in spectral data. When a new exoplanet is discovered, detecting water vapor is often one of the first observations attempted. Direct imaging challenges motivate indirect detection methods. Because direct imaging is so difficult, scientists have developed many alternative approaches to studying exoplanets. Transit spectroscopy, radial velocity measurements, gravitational microlensing, and other techniques all provide different pieces of information. Together, they build a comprehensive picture. The diversity of cosmic worlds hints at rich environments. Every exoplanet system is unique. Some have planets packed close together, others have planets spread far apart. Some have hot Jupiters, others have super-Earths. This diversity suggests that the galaxy is filled with a vast variety of environments, some of which may be suitable for life. Water-rich planets may host life in subsurface oceans. Even if a planet's surface is hostile, its interior may be hospitable. Subsurface oceans, protected from radiation and extreme temperatures by layers of ice, may provide stable, long-lasting environments where life could evolve. These hidden oceans may be among the most common habitats for life in the galaxy. As you rest here, consider how much we have learned and how much remains to discover. The observations we have made so far are just the beginning. Each new telescope, each new mission, each new technique reveals more about water in the cosmos. The story is still being written, and some of the most exciting chapters may lie ahead. Science progresses through the accumulation of evidence. No single observation can prove a theory. It takes many observations, made by different teams using different instruments, all pointing to the same conclusion. This is the strength of the scientific method. It is self-correcting, always open to new evidence, always willing to revise its conclusions in light of new data. The evidence for water on exoplanets has been building steadily for decades. Early detections were tentative, the signals barely distinguishable from noise. But as more observations accumulated, patterns began to emerge. Water vapor was detected on one planet, then another, then another. The techniques improved, the instruments became more sensitive, and the detections became more certain. Now, the presence of water in some exoplanet atmospheres is firmly established. This progress gives us confidence that we are on the right track. The universe is not barren and dry. Water exists in abundance on planets orbiting stars throughout our galaxy. The question is no longer whether water exists on exoplanets, but how common it is, in what forms it exists, and whether it is accompanied by life. Each new observation adds to the picture. A detection of water vapor here, a measurement of albedo there, a transit observation revealing atmospheric composition. Piece by piece, the puzzle comes together, revealing a cosmos rich in water and possibility. Segment 15. Clues and proxies. Sometimes we cannot detect water directly, but we can find other signs that point to its presence. These proxies and indirect indicators help us identify water worlds even when direct observation is difficult. They expand our ability to search and increase our chances of success. Studying icy planets provides clues to distant water worlds. The icy moons and dwarf planets of our own solar system are natural laboratories. By studying them, we learn what icy worlds look like, how they behave, and what signatures they produce. This knowledge helps us interpret observations of distant exoplanets. Future missions will sample cryovolcanic plumes. The plumes of Enceladus have already been sampled by Cassini, and future missions will go even further. Detailed chemical analysis of plume material could reveal the presence of complex organic molecules or even signs of life. These missions represent our best near-term opportunity to search for life beyond Earth. The quest for water in space inspires curiosity and discovery. Beyond the scientific value, the search for water captures the human imagination. Water is essential to our own lives, and finding it elsewhere connects us to the cosmos in a profound way. The quest for water is part of the larger human quest to understand our place in the universe. Water ice on exoplanets can be detected in far infrared wavelengths. The far infrared region of the spectrum is particularly sensitive to ice. At these wavelengths, ice has distinctive absorption and emission features that can be detected from great distances. Future telescopes operating in the far infrared will greatly expand our ability to detect ice on exoplanets. White dwarfs may host detectable icy disks with water ice. When a star like our Sun dies, it becomes a white dwarf, a dense, fading ember. Some white dwarfs are surrounded by disks of debris, the remnants of planetary systems. These disks may contain water ice, which can be detected through infrared observations. Rotational lines in the infrared spectrum reveal water vapor. Water molecules rotate and vibrate in characteristic ways, and these motions produce distinctive patterns in the infrared spectrum. By detecting these rotational lines, astronomers can identify water vapor even in very thin atmospheres or in the cold reaches of interstellar space. Enhanced spectrometers like PRIMA improve water detection. The instruments we use to detect water are constantly being improved. Each generation of spectrometers is more sensitive, more precise, and more capable than the last. PRIMA and other future instruments will revolutionize our ability to find water throughout the cosmos. Radar instruments can find buried water ice on planetary surfaces. On worlds like the Moon and Mars, water ice may be buried beneath the surface, invisible to optical telescopes. Radar can penetrate the soil and detect these hidden deposits, revealing water that would otherwise remain unknown. Cosmic rays generate radar waves that bounce off subsurface ice. This elegant technique uses natural cosmic rays as a source of radar waves. When these rays strike a planetary surface, they create brief pulses of radio waves that penetrate the soil. Any buried ice reflects these waves, creating echoes that can be detected by sensitive instruments. Lunar water ice detection helps sustain future lunar missions. The water ice buried in the permanently shadowed craters of the Moon is not just scientifically interesting, it is practically valuable. Future lunar missions will need water for drinking, for growing food, and for making rocket fuel. The Moon's ice could support a permanent human presence beyond Earth. As you continue to rest, let these indirect methods of detection fill your awareness. The universe reveals its secrets through many channels: light and radio waves, infrared and ultraviolet, direct observation, and subtle inference. Each provides a piece of the puzzle, and together they paint a picture of a cosmos rich in water and possibility. The art of scientific inference is subtle and nuanced. We cannot always observe what we want to observe directly. The universe is vast, our instruments are limited, and some phenomena are inherently difficult to detect. In such cases, we must rely on proxies, on indirect indicators that point toward the truth without revealing it directly. Consider how we infer the presence of subsurface oceans on icy moons. We cannot see these oceans directly. They are hidden beneath miles of ice. But we can observe the geysers that erupt from the surface, the magnetic fields that suggest a conducting layer beneath the ice, the tidal flexing that indicates a liquid interior. These indirect observations taken together provide strong evidence for hidden oceans. We have never seen these oceans, but we are confident they exist. The same approach applies to exoplanets. We may not be able to see liquid water on a distant world directly, but we can observe water vapor in the atmosphere, measure the reflectivity that suggests ice, detect the chemical signatures that imply oceans are sequestering carbon dioxide. Each piece of evidence adds to our confidence, building a case for water that may one day be confirmed by more direct observations. This is how science often works. We start with indirect evidence, build hypotheses, test those hypotheses against new observations, and gradually converge on the truth. The process can be slow, spanning decades or even centuries, but it is reliable, and it leads us ever closer to understanding the universe we inhabit. Segment 16. Atmospheric signatures. The atmospheres of exoplanets carry information about the worlds they envelop. By studying these atmospheres, we learn about surface conditions, climate patterns, and the presence of water in its various forms. Tonight we examine the atmospheric signatures that guide our search. A decrease in atmospheric carbon dioxide may indicate surface oceans. This indirect method of detecting water relies on the chemistry that occurs when water and carbon dioxide interact. Oceans absorb carbon dioxide, reducing its concentration in the atmosphere. When we observe a planet with unexpectedly low carbon dioxide levels, it may suggest that oceans are present. Water dissolved in oceans sequesters atmospheric carbon dioxide. The process is called carbon sequestration, and it has been occurring on Earth for billions of years. The carbon dioxide dissolves in seawater, reacts with minerals, and eventually becomes locked away in carbonate rocks on the ocean floor. This process has helped regulate Earth's climate and may operate on other water worlds as well. Telescopes like JWST measure carbon dioxide to infer surface water. The James Webb Space Telescope has the sensitivity to measure carbon dioxide and other gases in exoplanet atmospheres. By analyzing these measurements, scientists can draw conclusions about conditions on the surface below. A planet with low carbon dioxide and water vapor may be a strong candidate for having surface oceans. Machine learning algorithms aid in identifying water signatures. The amount of data generated by modern telescopes is staggering. Machine learning algorithms help process this data, finding patterns and signatures that human researchers might miss. These algorithms are becoming essential tools in the search for water. Spectral data can distinguish ice, water vapor, and clouds. Each form of water has its own spectral signature. Ice absorbs and reflects light differently than vapor, and vapor differently than liquid. By carefully analyzing spectral data, we can determine not just that water is present, but in what form and in what quantity. Reflectance and color reveal surface features like oceans and ice caps. The overall brightness and color of a planet contain information about its surface. An ocean world would appear different from a desert world, and both would appear different from an ice-covered world. These differences can be detected even from enormous distances. Algorithms simulate surface and atmospheric compositions. Computer models are essential for interpreting observations. By simulating many different combinations of surface and atmospheric conditions, scientists can determine which combinations best match the observations. This process narrows down the possibilities and helps identify the most likely conditions on distant worlds. High albedo reflections help identify planets with resurfaced ice. When a planet is unusually bright, it may indicate that fresh ice covers the surface. This fresh ice could have been deposited by recent cryovolcanic activity. The brightness is a clue to geological processes occurring on the world. Variations in reflectance spectra suggest cryovolcanism. If a planet's brightness changes over time, it may indicate that the surface is being renewed. Cryovolcanic deposits would increase brightness temporarily before weathering and darkening over time. These variations can be detected through careful, long-term monitoring. Gas absorption features during transits indicate water vapor. Transit spectroscopy remains one of the most powerful tools for detecting water. When a planet transits its star, starlight filtering through its atmosphere carries the chemical fingerprints of the gases present. Water vapor, with its distinctive absorption features, can be identified in this filtered light. As you rest here, consider how much information is carried in light. Every photon that reaches our telescopes has a story to tell. It has traveled for years or centuries, been absorbed and re-emitted, filtered and scattered. And in its wavelengths and intensities, it carries news of distant worlds, of atmospheres and surfaces, of water in all its forms. Light is our window on the universe. We cannot touch the stars, cannot taste their atmospheres, cannot feel the heat of their fusion fires. But we can see them, and in that seeing lies all our knowledge of the cosmos. The light that reaches us from a distant star has traveled unchanged across the void, carrying information from its source like a message in a bottle. When that light passes through a planet's atmosphere, it picks up information about that atmosphere. Some wavelengths are absorbed by gases, leaving gaps in the spectrum. Other wavelengths pass through unchanged. By analyzing this filtered light, we can determine what gases are present, how much of each gas exists, and even something about the temperature and pressure of the atmosphere. This is the magic of spectroscopy, one of the most powerful tools in astronomy. A spectrometer separates light into its component wavelengths, like a prism creating a rainbow. The resulting spectrum is like a fingerprint, unique to the particular combination of elements and compounds that produced it. By reading this fingerprint, we can learn about objects we will never touch, never visit, never directly experience. The spectrum of water vapor is particularly distinctive. It has strong absorption features at specific wavelengths in the infrared, creating unmistakable patterns that can be recognized even in noisy data. When we detect these patterns in the light filtered through an exoplanet's atmosphere, we know that water vapor is present. The detection is certain, the evidence is clear, and our understanding of that distant world is transformed. Segment 17. Cryovolcanism in depth. Cryovolcanism is one of the most fascinating geological processes we have discovered beyond Earth. These ice volcanoes, erupting water and other frozen materials into space, reveal hidden oceans and active interiors. Tonight, we explore this process in greater depth. Cryovolcanism produces high H2O column densities. During an eruption, vast amounts of water vapor are released. The concentration of water in a column of space above the eruption spikes dramatically. This spike can be detected through spectroscopic observation, revealing the intensity and scale of the eruption. Direct imaging reveals spectra of surface oceans. As imaging technology improves, we may be able to capture direct images of exoplanet surfaces. The spectra of these images would reveal the composition of the surface, including any liquid water that might be present. This capability is still being developed, but it represents an exciting frontier. Indirect methods include anomalously high reflectivity. Sometimes the evidence for cryovolcanism is indirect, a world that is brighter than expected or that shows variations in brightness over time may be experiencing surface renewal from volcanic activity. These indirect indicators help us identify active worlds. Cloudy, water-rich atmospheres produce specific spectral features. The aftermath of cryovolcanic eruptions may include clouds of water ice particles in the atmosphere. These clouds have distinctive spectral signatures that can be detected from afar. They provide evidence of recent volcanic activity and the presence of subsurface water. Water-rich exoplanets are prime for habitability studies. Every exoplanet with detected water becomes a priority target for further study. These are the worlds most likely to support life, and they receive the most attention from astronomers and astrobiologists. The detection of water is often the first step in a long process of characterization. Water vapor plumes help infer subsurface oceans. The plumes we observe erupting from icy moons are direct evidence of liquid water below. The water must come from somewhere, and that somewhere is an ocean hidden beneath the ice. These plumes are windows into environments we cannot otherwise observe. Water vapor emissions indicate geological activity. The emission of water vapor requires energy. That energy must come from somewhere, whether from tidal heating, radioactive decay, or some other source. The presence of water vapor emissions tells us that a world is geologically alive, that processes are occurring that might support chemistry and life. Cryovolcanic eruptions transport water to the surface. This transport is crucial for the search for life. If microbes exist in a subsurface ocean, cryovolcanic activity might carry them to the surface. There, they might be detected by spacecraft, or their chemical signatures might be identified in plume material. Cryovolcanism creates opportunities for detection. High albedo features suggest recent resurfacing. Fresh ice is bright. When we observe areas of high albedo on an icy world, we know that fresh material has been deposited recently. This fresh material likely came from the interior, carried by cryovolcanic processes. The bright patches are maps of geological activity. Spectroscopic observations identify solid ice layers. The spectra of ice can reveal its crystalline structure, its purity, and its age. Fresh ice looks different from ancient ice. By studying these spectra, we can learn about the history of an icy surface and the processes that have shaped it. As you drift here in this peaceful moment, imagine standing on the surface of an icy moon. In the distance, a plume of ice crystals rises from a crack in the surface, glittering in the dim light of a distant sun. This eruption is driven by an ocean far below, an ocean that has existed for billions of years, an ocean that might just possibly harbor life. These are not fantasies. These are the realities of worlds in our own solar system, and perhaps of countless worlds beyond. Cryovolcanism is one of the most visually spectacular phenomena in the outer solar system. The geysers of Enceladus erupt hundreds of kilometers above the Moon's surface, sending ice crystals spiraling into space, where they eventually become part of Saturn's rings. The process is driven by heat, generated as Saturn's gravity stretches and compresses the Moon's interior. This heat melts ice deep within Enceladus, creating pockets of liquid water that periodically erupt to the surface. The eruptions are not continuous. They vary in intensity over time, influenced by tidal forces that change as Enceladus moves through its orbit. At some points in its orbit, the Moon is stretched more intensely, generating more heat and triggering more vigorous eruptions. At other points, the tidal forces are weaker, and the eruptions subside. This variability provides clues to the internal structure of the Moon and the processes occurring within. Similar processes may occur on exoplanets throughout the galaxy. Icy worlds orbiting close to giant planets would experience tidal heating, just as Enceladus experiences heating from Saturn. If these worlds have subsurface oceans, they might exhibit cryovolcanic activity, erupting water and ice into their atmospheres or into space. Such activity could be detected from afar, providing evidence of liquid water on worlds we will never visit. The detection of cryovolcanism on an exoplanet would be enormously exciting. It would tell us that the planet is geologically active, that liquid water exists beneath its surface, and that heat is being generated in its interior. All of these are favorable conditions for life. A cryovolcanically active exoplanet would immediately become a priority target for further study. Segment 18. The search continues. Our journey through the quiet worlds of water and ice draws toward its close, but the search itself continues. Every day, astronomers point their telescopes toward distant stars, seeking evidence of water on worlds we have only begun to explore. The quest is far from over. Water vapor detection reveals atmospheric composition during transits. Each transit observation adds to our knowledge. The data accumulates, patterns emerge, and our understanding deepens. What seems like faint, ambiguous signals today may become clear detections tomorrow as our analysis techniques improve. Direct detection of liquid water is advancing. The ultimate goal is to detect liquid water on a planetary surface directly. This remains difficult, but progress is being made. New telescopes, new instruments, and new techniques are bringing this capability within reach. the first direct detection of an exoplanet ocean may occur within the coming decades. Multiple methods increase confidence in water detection. No single observation is definitive, but multiple independent lines of evidence build a compelling case. When transit spectroscopy, reflectance measurements, climate models, and indirect indicators all point to the same conclusion, we can be confident that water is present. Future missions will explore icy, watery exoplanets. The missions being planned today will transform our understanding of water in the cosmos. Space telescopes with unprecedented capabilities, probes designed to sample cryovolcanic plumes, landers that will drill through ice to reach hidden oceans. The future of water exploration is bright. Ocean worlds are analogues for icy exoplanets. Europa, Enceladus, and other ocean worlds in our solar system help us understand what we might find among the stars. By studying these nearby worlds, we prepare for the discoveries that await us when we turn our attention to exoplanets. Subsurface oceans may harbor microbial life. The possibility of life in hidden oceans is one of the most exciting prospects in all of science. If we find life in the ocean of Europa or Enceladus, it will prove that life can arise independently on different worlds. This discovery would transform our understanding of biology and our place in the universe. Water ice layers insulate subsurface oceans. The ice that covers these oceans is not just a barrier, it is a protective blanket. It shields the ocean from radiation, prevents evaporation, and maintains stable conditions over billions of years. This insulation makes long-term habitability possible. Tidal forces induce geysers and eruptions. The gravitational dance between moons and planets generates the heat that keeps subsurface oceans liquid. This tidal heating is a source of energy that can drive geological activity and potentially support life. Without it, these oceans would freeze solid. Eruptions can be observed remotely. The geysers of Enceladus, the possible plumes of Europa, the water vapor around distant exoplanets, all can be observed from afar. Remote observation allows us to study worlds we cannot visit, at least not yet. Each observation adds to our understanding. Cryovolcanic activity is key in habitability studies. The presence of cryovolcanism tells us that a world is active, that liquid water exists, that heat is being generated, and that materials are being cycled. All of these factors contribute to habitability. Cryovolcanism is a key signature in the search for life. As you rest here, know that the search continues even now. Somewhere, an astronomer is analyzing data from a distant exoplanet, searching for the signature of water. Somewhere, an engineer is designing a spacecraft that will one day fly through a cryovolcanic plume. Somewhere, a student is learning about water worlds for the first time, beginning a career that may lead to discoveries we cannot yet imagine. The search for water is a human endeavor, carried forward by countless individuals working together across generations. The beauty of this search is that it unites us. People from every nation, every culture, every background contribute to the effort. Telescopes in Chile and Hawaii, in space and on the ground, all gather data that flows into a common pool of knowledge. Computer programmers develop algorithms. Engineers build instruments. Students analyze data. Teachers inspire new generations. The search for water on exoplanets is a truly global endeavor, a testament to what humanity can accomplish when we work together. And the search is accelerating. New telescopes are being designed and built, each more capable than the last. The James Webb Space Telescope, launched in 2021, has already begun to reveal the atmospheres of exoplanets in unprecedented detail. Future telescopes, still in the planning stages, will go even further, potentially allowing us to detect signs of life on distant worlds. We live at a pivotal moment in history. The first generation that might discover life beyond Earth is alive today. The first generation that might explore the subsurface oceans of Europa or Enceladus is growing up right now, dreaming of the worlds they might one day visit. The search for water is not just about science. It is about our future as a species, about the expansion of human knowledge and human presence into the cosmos. The discoveries we make in the coming decades may transform our understanding of life, of our place in the universe, of what it means to be human. The search for water is a search for answers to our deepest questions. And the answers, when they come, will be worth the wait. Segment 19. Promising Targets. As our ability to detect and characterize exoplanets improves, certain worlds emerge as particularly promising targets. These are the planets and moons where water seems most likely, where conditions might be right for habitability, where the search for life might one day succeed. Plumes may contain salts and chemicals. The material erupting from cryovolcanic plumes is not pure water. It contains dissolved salts, organic compounds, and other substances that provide clues to conditions in the ocean below. These chemicals are potential signatures of habitability, perhaps even of life itself. Future missions will sample plumes directly. Missions like Europa Clipper and potential future Enceladus orbiters are being designed to study these plumes in detail. Advanced instruments will analyze plume material, searching for the complex molecules that might indicate biology. These missions may provide our best near-term opportunity to search for life beyond Earth. Water worlds beyond our solar system are promising. The exoplanets we have discovered include many potential water worlds. Some orbit in the habitable zones of their stars, where liquid water could exist on their surfaces. Others may harbor subsurface oceans, warmed by internal heat. These worlds are high priorities for further study. Many exoplanets are in the habitable zone. The catalogue of known exoplanets includes hundreds in the habitable zones of their stars. Not all of these are water worlds, but some may be. As our ability to characterize these planets improves, we will identify the most promising candidates for habitability. Analyzing starlight reveals water signatures. The light from distant stars, filtered through the atmospheres of transiting planets, carries information about those atmospheres. Water vapor leaves distinctive absorption features in this light. Detecting these features tells us that water is present, making the planet a priority for further investigation. Water vapor absorption lines indicate water presence. The absorption lines of water vapor are strong and distinctive. They appear at specific wavelengths in the infrared, creating patterns that can be recognized even in noisy data. These patterns are one of the main tools we use to detect water on exoplanets. Clouds of water vapor provide clues to habitability. The presence of water clouds indicates that water is abundant, that temperatures allow for evaporation and condensation, and that the planet has an active water cycle. These are promising signs for habitability. Surface water greatly increases habitability potential. A planet with liquid water on its surface has met one of the most important conditions for life. Surface water allows for photosynthesis, for diverse ecosystems, for the kind of complex biosphere that has evolved on Earth. Surface water worlds are premium targets. Planets with stable oceans are promising for life. Stability is crucial. Life needs time to evolve, and evolution requires consistent conditions. A planet with oceans that have persisted for billions of years is more likely to have developed complex life than one with volatile conditions. Water-rich planets may have thick atmospheres maintaining liquid water. The atmosphere and the ocean work together. A thick atmosphere traps heat. A water-rich atmosphere adds to this greenhouse effect, and together they maintain conditions suitable for liquid water. These factors combine to create potentially habitable environments. As you rest here, consider which of these distant worlds might be the first to reveal signs of life. Perhaps it will be a planet in the habitable zone of a nearby red dwarf, detected through transit spectroscopy. Perhaps it will be an icy moon in our own solar system, sampled by a future spacecraft. Wherever the discovery is made, it will represent one of the most profound moments in human history. The moment we learn that we are not alone. The most promising targets for the search for life are those where we have already detected water. These worlds have passed the first test. They possess the one ingredient we know is essential for life as we understand it. Now the question becomes, what other conditions are present? Is there energy? Are there nutrients? Is there stability? Some targets are close enough to study in detail. Europa and Enceladus, moons in our own solar system, are within reach of spacecraft that could fly through their plumes, land on their surfaces, or even drill through their ice. These nearby worlds may provide our first opportunity to search for life beyond Earth, to analyze alien chemistry, to look for the signatures of biology in an extraterrestrial environment. Other targets are farther away, requiring different approaches. The exoplanets we study through transit spectroscopy and direct imaging are too distant to visit with current technology. But we can still learn a great deal about them from afar. Their atmospheres can be analyzed, their surfaces can be characterized, and their potential for habitability can be assessed. Some of these distant worlds may be home to life that we can never directly contact, but might nonetheless be able to detect. The list of promising targets grows with each passing year. New exoplanets are discovered, new moons are characterized, new techniques reveal water in unexpected places. The search broadens and deepens, encompassing more and more of the cosmos. Somewhere among these targets, life may be waiting to be discovered. Segment 20. The Endless Frontier. We come now to the end of our journey, but the cosmos stretches on forever. The quiet worlds of water and ice we have explored tonight are just a fraction of what exists out there, waiting to be discovered. As you prepare for sleep, let these final thoughts accompany you into dreams. Improved detection techniques will reveal more water worlds. Every year brings advances in telescope technology, in data analysis methods, in our theoretical understanding. These advances will reveal water worlds we cannot yet detect. The catalogue of known water worlds will grow, and with it, our understanding of habitability in the cosmos. Water distribution in the cosmos informs planetary evolution. The patterns of water distribution tell us about how planetary systems form and evolve. Water is delivered by comets and asteroids, concentrated by planetary migration, lost through atmospheric escape. Understanding these processes helps us predict where water worlds might exist. High-pressure ice layers may separate oceans from the surface. The structure of water worlds can be complex, with oceans sandwiched between layers of ice at different pressures. These structures affect habitability and create unique environments that we are only beginning to understand. Ice layers can act as barriers, isolating subsurface oceans. An ocean completely enclosed by ice may evolve in isolation for billions of years. Whatever life might arise in such an ocean would be utterly alien, shaped by conditions unlike anything on Earth. These isolated oceans are among the most intriguing environments in the cosmos. Surface ice is renewed by cryovolcanic activity on some moons. The surfaces of icy worlds are not static. They are renewed, refreshed, reshaped by geological processes driven from within. This activity reveals the presence of liquid water and the possibility of habitability. Ice shell composition affects the likelihood of life. The ice that covers a subsurface ocean is a record of the ocean's chemistry. By studying this ice, we can learn about conditions in the ocean below and assess the likelihood that life could exist. Observations suggest some planets have warm, water-rich surfaces. Not all water worlds are frozen. Some may have conditions similar to Earth's, with liquid oceans under open skies. These warm water worlds are particularly exciting targets, as they may support surface-based ecosystems. Spectral analysis and modeling help identify water worlds. The combination of observation and theory allows us to identify water worlds with increasing confidence. As our models improve and our observations accumulate, our picture of water in the cosmos becomes clearer. Future telescopes will distinguish fresh water from salty oceans. The next generation of telescopes may have the precision to detect the subtle differences between fresh and salt water. This capability would add another dimension to our understanding of distant oceans. Water worlds are among the most intriguing cosmic targets. In the vast diversity of exoplanets, water worlds stand out. They are the most likely to support life as we know it. They are the most similar to our own Earth. They represent our best hope for finding kinship in the cosmos. As you drift now towards sleep, carry with you the wonder of these water worlds. Somewhere in the darkness between the stars, oceans may be catching starlight. Ice caps may be gleaming white under unfamiliar suns. Geysers may be erupting, sending plumes of water into space. Life, in some form we cannot yet imagine, may be swimming through alien seas. You are a child of Earth, a water world among water worlds. The same molecules that make up your body exist throughout the cosmos, in the ice of distant moons, in the vapor of exoplanet atmospheres, in the potential oceans of worlds we have only begun to explore. You are connected to all of this, part of a universe filled with water and ice, possibility and wonder. Rest now. Let the quiet worlds drift through your dreams. Tomorrow, the search continues. But tonight, the cosmos holds you gently, a drop of water in an infinite sea of stars. Good night, dear traveler. Sleep well.